Okay, so before we jump into the second law, I wanted to cover a little bit what we missed out on in terms of the balance equations for the first law. So the first law of balance equations see, I'm not doing very good with this writing here. Da-da-da-da. So, the first law is just law of conservation of energy. So all we're trying to do here is organize how much energy is coming into a particular system and how much energy is coming out of a system. So what we will typically write is du dt, right? That is the change in total internal energy of the system with respect to time. So in a steady state process, what should that equal? Zero, right? On a steady state process, the amount of energy coming in is equal to the amount of energy coming out. So the key thing is when you hear steady state, anything with a dt is zero. Not d temperature, but d time. So that's the main key word there. So when we're keeping track of everything that's coming into and out of a system, we could have multiple flow streams. I'll call them K. So summing from K equals 1 to big K, the total number of streams coming into a system. We'll have a mass flow rate of that particular K stream coming in. And we're going to sum up all of the different types of energy that that particular stream can bring in. So we could have enthalpy, and we'll talk a little bit more about that. Now the hat here, change colors. So the H hat is going to be equal to a joules per kilogram. And oftentimes we'll also write maybe H underbar is equal to joules per mole, for example. I may mess up on the nomenclature a little bit, so just recognize if there's a hat or an underbar, I mean specific. And that hopefully I'll try and keep the hat and the underbar consistent through the lectures, but just know that, you know, it goes from sort of an extensive property to an intensive property. Instead of the total energy, it's how much energy per unit volume. So it's kind of like volume versus density. Okay. So when you times by the mass flow rate, which is going to be some sort of mass per unit time, times that by energy per unit mass, that gives us total units of energy per unit time flowing into the system. So a rate of power input in the form of enthalpy. Then we can also have kinetic energy, V squared over 2. 1/2 mv squared. That gives us the kinetic energy coming into the system. And we can also have various forms of potential energy, which I'm just going to write here as big psi. Or phi. I'm not sure. One of the two. Whatever that Greek letter is. So for every stream coming into it, the mass brings with it enthalpy in the form of chemical bonds, bond vibrations, molecular motion. It brings with it its kinetic energy in terms of the bulk fluid flow. Now that's not the molecular fluid motion. That's going to be the enthalpy. And also any potential energy that comes within the system. In general, we are going to neglect the kinetic energy and potential energy. It's much, much smaller than the enthalpy. We can also have various streams of heat coming into the system and various forms of work coming into the system. Now, oftentimes when you see the balance equations written out, there's just one Q and one W. But no, that's just all of the heats and all of the works in case you have multiple sources. So for work, we can write it usually as two different ways, which is shaft work, WS, which is going to be if there's an impeller or a turbine or something like that, that's either inputting work or extracting work out of the process. And you can also have system expansion work. So P dV dt. Right? So if you have a system and its volume is increasing, right, it has to be losing energy. Because that system volume has to push back the surrounding atmosphere, and in order to push back the surrounding atmosphere, that takes energy. Right? So you can have expansion work and you can have shaft work. But this is the common sort of starting point that we would use in a chemical engineering sort of balance or mechanical engineering balance on a particular process. Reactor, separator, mixer, heat exchanger, everything would fall under this category here. So let's talk really quickly about enthalpy. So H is defined as U plus PV. Now this is entirely a unit of convenience. So we've already seen that the enthalpy shows up in the open system mass balance, or sorry, open system energy balance. So let's take a brief second as to why we care about that. So if we are to draw out an open system where we have a pipe coming in, we have a system, and we have a pipe coming out. The reason why we care about enthalpy is because the matter in the pipe will not spontaneously just go into the system, right? It has to be pushed. So a way to think about this here is we've got some volume in and some volume out, and there has to be a pressure pushing in and a pressure out. So P1 or P out. Hopefully that's legible. Okay. So within this volume is some sort of mass. So in order to flow material, you physically have to push it into the system. So just the same way that if you compressed a system, you would be putting energy to it. If you expanded a system, you'd be taking energy out of it. It's exactly the same way that flowing material into a system works. So work in this case here, is equal to P1 or Pn V hat 1 delta M1. So if you look at the units here, pressure is equal to pascals. We have volume, which is meters cubed per kilogram. And for mass, we have kilograms. So what is a Pascal meter cubed? Almost.
Joule.
Joule. It is energy. So P times V is units of energy. So by pushing with a pressure in, a unit of volume, you're squeezing energy into the system. And then the work out, minus P2 V hat 2 delta M2. Okay, so if we then relate this back to the expression that we had previously here, right? We want the total work going into the system from the mass flow rate stream. That is the summation of, actually no, these don't have to be in and out. We're doing the total summation. So summing up all the streams, we have a mass flow rate, we have internal energy coming into the system, we have PV coming into the system, right, because you're physically pushing it in, and we have the velocity and potential energy. So we can write this instead as a summation of we can just combine the U and the PV. And that's where we get the enthalpy term from. So in an open system, most all of the energy in enthalpy comes from the internal energy. That PV is just a little bit extra. So if you were to go your entire life, only using U and never using H, it might not come back to burn you too bad, unless you're going to systems that are really high pressure or conditions like that. But the U contains all the information from the molecular motion, but it doesn't contain the collective sort of motion or PV sort of work that's going on there. So most everything's contained in the U. But this is why we use enthalpy, is because in order to get material to flow into a system, you have to do a little bit extra work to push it in there. Hopefully that makes sense. Any questions? So with this up here, we can do most all of basically sort of a mechanical engineering type thermodynamics class. We could do pumps, cycles, heat exchangers. For cycles, we do need a little bit of the second law. But anyway, so this these equations, basically this equation here, right, this is what we can use to solve most of this week's homework. But the key thing is just knowing how to apply this equation, right? How do you calculate work? How do you calculate Q? What's an open system? What's a closed system? So just very quickly, if it's a closed system, what goes to 0 in this expression? Mk goes to 0. There's no mass in, there's no mass out. If it's a steady state system, what goes to 0? Okay, and if it's an adiabatic system, what goes to 0?
Q.
If it's a rigid wall, what goes to 0? Exactly. So this one equation here can be simplified down to a piston-cylinder device, to a heat exchanger, to a compressor, to a turbine, to everything. And so hopefully this is not new to anyone in the class. Okay. So now let's move on, and let's talk about the second law. Okay. So we'll go over a couple of historical statements of the second law of thermodynamics, and then we'll relate it to kind of how we modernly apply the second law.
Just have one quick question on the homework. We can neglect kinetic energy and potential energy, right?
Yes, in general, I will hardly ever mention kinetic and potential energy again.
Yeah.
Unless I come up with I may come up with a problem on a quiz or an exam that says, you know, gravitational potential energy is rho gh. I give you the formula. Let's say I drop a ball from a mile above and it hits the ground. How much energy does it release or something like that? That could be a type of problem I would answer or I'd ask, but I would give you the kinetic potential energy equation is rho gh, h is a mile, and so on and so forth. So you may need to know how to apply it, but in general we're going to focus mostly on just enthalpy.
I have a question.
Yeah, sure.
So why don't we put everything in the W dot term, the work that we are doing, instead of why do we split it up into enthalpy and another work term?
Just convenience, I think. It's easier to tabulate it with enthalpy. So enthalpy has sort of been ingrained into this sort of the framework of thermodynamics. And so that's why we, at least in chemical engineering textbooks, we typically tabulate C sub P. So if we tabulate C sub P, and it'll be more clear as we move forward why we use enthalpy more than internal energy. But basically because it's easier for us to do experiments in like a constant pressure environment than a constant volume environment. So it's actually easier for us to measure enthalpy than it is internal energy. So that's one of the main reasons why, is that when we tabulate the results, it's easier to actually measure H than it is U. Just because maintaining a constant temperature and constant pressure is a lot easier, and those are the base units of enthalpy. But we'll talk about that when we go into the mathematics a little bit more.
So the W dot term, that should have other work that is being done on the system?
Yeah, so let's rehash that a little bit. So the W dot term here. So this is, when we talk about, I guess let's talk about this expression down here. The shaft work is going to be like if you're extracting energy from like a turbine, for example. You bring in superheated steam and it leaves saturated steam, right? Which, for example, is one of the homework questions. How much work can you get out of the system? Well, we don't care about the design of like the turbine or its blades or anything like that, right? We're just knowing that it's somehow pulling the work out. Now in terms of, so that's the shaft work. So the shaft work, we're never going to calculate it from anything other than an energy balance. Now this PV work right here, this is really commonly done in a piston cylinder device. So we may be doing, you know, some integration of V over T, or you substitute in an equation of state and then integrate it and things like that. So in that case, this PV is the overall system expanding here, the box of the overall system getting bigger. But in terms of when fluid flows into the system, it's just easier if we count that energy in the form of the H. So it's just a matter of convenience. But in theory, again, you could reformulate all of these in a different way.
Thank you.
Mm-hmm. Any other questions on the first law?
Can we use D tables to calculate the work?
Oh yes, absolutely. So what we're trying to do, for this first homework is mostly focus on tabulated data, and then we'll transition into calculating, you know, real data. So yeah, absolutely. If you have tabulated data, it is by far the most accurate. So always use tabulated data if it's available. Okay, second law. Let's go through a couple of historical statements. So one of the earliest is Clausius, as in the Clausius-Clapeyron equation. And this is in 1854. And I'll paraphrase this a little bit, but basically he is saying heat cannot go from cold to hot. So schematically, we will draw this out. If we have a hot reservoir and a cold reservoir, and we have a Q, this is not possible. If TH is greater than TC. But we're already seeing some flaws in this assignment here because in order to define the second law, we've had to rely on the concept of temperature and on the concept of heat. So it's not a very rigorous mathematical definition. Right? It's more of a phenomenological definition of the second law. Oh, sorry, let everyone get all this down. Okay, so moving forward in the future, both Kelvin and Planck so Kelvin in about 1851 and Planck in about 1897 both formulated similar versions of the second law, and that was you cannot directly convert heat to work. So to draw this out, we could have a hot reservoir, and we could have a system where you don't know what this system is. It could be some magical apparatus. Right? So in the case, we see this often a lot in like the Carnot cycle. You just draw a circle and that's the process. Right? That could be a heat engine or, well, it has to be a heat engine, but it could be internal combustion or whatever the case is, right? So we have a Q coming into this process, and we have work coming out of it, and basically this is not possible. Right? Because if we were to look at this cycle here, if we were to do an energy balance on this process, energy balance works out perfectly fine, right? It's steady state, so du dt is equal to 0, which would mean that the Q is equal to the W, right? So from an energy balance perspective, this is totally fine. You're directly converting heat to work. Energy is conserved. But the second law says this is not possible. Again, now this definition has temperature, heat, and work, all lumped into the second law. Again, not a very uniform and stable, or not a very consistent definition. So then in 1909, an individual named Carathéodory, he came up with a sort of a fundamental mathematical framework to derive the second law. And these efforts are still going on basically to this day. You know, I reviewed a paper when I was sort of getting ready for this class years ago by a group in 1999 that is still trying to come up with a nice, consistent framework for the second law. It's an interesting framework to look at. And it really boils down like the key properties of entropy that are required for it to exist in its current way, but it's not really worth our time because it's a bit sort of a fundamental mathematical approach. So Carathéodory basically boiled down the second law to a much more abstract form. So I'll actually write it out because I don't have quite as good of a way to paraphrase it. So So in any neighborhood of any state, so we use this term a lot in thermodynamics of a state. So a state of matter is like a particular unit of temperature, pressure, and phase, right? So the state of the air in this room is at like, I don't know, 20 degrees C, 1 atmosphere, right? And it's a gas phase, right? That's a state. So if I wanted to take a volume of that and transition to a different state, that would mean I would either change its phase, change its temperature, or change its pressure. So a state is the collection of variables that describe everything that you need to know about that system. So that's what we use by states. We use that term quite a lot. Okay, so in any neighborhood of any state, there are states Okay, so in any neighborhood of any state, there are states that cannot be reached by an adiabatic process, basically saying that some things cannot spontaneously change. So in other words, you cannot spontaneously go from a low energy state to a high energy state. There are just some states that you just cannot reach. And it depends on basically what are the properties of entropy to determine which states you can and cannot reach. So basically, this is sort of a cyclic logic saying that you cannot violate the second law. And there's a lot of math that goes into making these seem a lot fancier than sort of the silly statement itself. We're not going to go into too much of those details. But basically, a lot of the properties that I've already stated for entropy, like its entropy is extensive. It is... so extensive means matter carries entropy. It is additive. It is concave. So all of these properties of entropy sort of come out of these really fundamental mathematical ways of writing the second law. But the exact details are not particularly useful for us in a practical perspective. But effectively, people are still trying to find nice, consistent, uniform ways to derive the second law without having to rely on notions of temperature, without having to rely on notions of heat or work or anything like that. Okay. So what I'd like to do now is go over, how do we get this expression? ds dt is equal to q dot over t plus S dot gen. So this is an entropy balance of a closed system that we would maybe have seen before in an undergraduate thermodynamics class. How do we go from Clausius's definition or Kelvin's definition of the second law to this equation? So it's not quite apparent where does this Q over T thing come from, because none of the definitions that we talked about already have this. So let's use a more basic starting point of the second law and then work towards deriving this expression here. So we're going to construct an artificial system. We are going to have an infinite reservoir. So the temperature in the surroundings is going to be constant. And we're going to have a system contained on the inside that is going to have a particular temperature. It's going to have a particular volume, which is going to be constant. So if the volume's constant, that means we have rigid walls, which means the only way to transfer energy into this system is in the form of heat. So there's no work being done on the system. And it has a particular internal energy. So this is supposed to be U with Roman numeral I's. I'm going to upgrade my hardware so that we'll have better resolution in the future. Okay, so this is the system that we've constructed. So what we're going to do is we're going to focus in on doing an entropy balance and energy balances on these processes to see if we can get the expression in the upper left-hand corner. So let's do an overall first law. Okay, so the first law, I'm going to omit the dt. Right, so this is du dt, but we're just going to say du, right, because it could be over any arbitrary unit of time. Okay, so what is the overall change in energy of the entire universe that we've drawn on the page?
0.
0, right? Energy is conserved. We're not creating it, we're not destroying it. So the overall energy balance is 0, which is equal to how much does du of the system change compared to du of the surroundings, right? Any energy that's lost by the surroundings is gained by the system, which means that the total energy of this arbitrarily small universe or infinite universe that we've created is maintained constant. So in other words, du of I is equal to minus du of the surroundings. Okay, so now let's do a first law balance on the system. So du of I is equal to what? It's a closed system, so there's no mass flowing in or out. What is the only two ways that energy can get into this system? Okay, so we've got heat, and we've already sort of ruled out the other one, but in theory work could happen, but in this case we're saying no, there's no work going on in the process. Okay, so the next thing we're going to do is we're actually going to rely on the definition of temperature. So the definition of temperature is that 1 over T is equal to ds du at constant volume, which is convenient because we're at constant volume. So then we can use this expression to write that ds of the system is equal to du of the system divided by the temperature of the system. Again, thermomath, you can kind of play around a little bit with these differentials. And from our first law energy balance, this is equal to Q dot over T. We can also write from the definition of temperature that ds of the surroundings is equal to minus Q dot over T, right? Because du of the system is equal to minus du of the surroundings. Okay, so now let's use the most basic mathematical definition of the second law that we effectively have. And that is ds is greater than or equal to 0. Right? Entropy always either stays constant or it increases. That's basically the starting point that we have really for the second law. So from there, we can take advantage that ds, right, entropy is extensive and additive. Right? So if I take 1 bucket of water and 2 buckets of water and I pour it together, I'm basically increasing the entropy of that system. Right? The more material that I bring, the more entropy it brings with it. So ds for the entire universe is going to be equal to the change in entropy of the system plus the change in entropy of the surroundings. And we know that this is greater than or equal to 0. So if we substitute this expression down into here, actually rather, never mind, we want to substitute this expression down into here, we get that ds of the system minus q dot over t is greater than or equal to 0. And from there, we can just rearrange it. ds is greater than or equal to q dot over t, or ds of the system is equal to q dot over t plus the entropy generated, and S gen is greater than or equal to 0. And there we have it. Sort of the traditional starting point that we would use for an entropy balance in a typical thermodynamics class. Now, the only difference between this and what we may have seen in an open system is that we neglected the summation. In this case here, you notice I wrote this a little bit differently. I wrote this in terms of the molar entropy as opposed to the mass entropy, using the underbar as opposed to the hat. But I do ask that you be a little bit flexible in, if I draw a hat, maybe I meant molar sometimes, maybe I meant mass, but it should be hopefully clear in the context of the problem. So this is our typical starting point then if we were to do an entropy balance on a particular process. But this all comes from basically having to define temperature as how the entropy changes with U. Right? So that definition of temperature is critical for us to write the second law in really a useful form. Okay, so now we're going to take a brief couple minutes before class gets out, and we're going to use our combination of energy balances and entropy balances to reinvestigate the historical devices that were said to be not possible. So we're going to go to Clausius's device. So in this case here, we have a hot reservoir, TH. We have some magical process that we don't know what it is, but someone's making claims about it. We have heat coming into the cycle from the hot process, and potentially heat coming in from the cold side. Oops. I just drew it in that way just to make it, so the math should work out. So ultimately, when you do these energy balances, a lot of people stress a bit much about whether work is positive going into the system or positive going out of the system. I never care that much. All I care about is that whichever way you draw your arrow, you're consistent in your own energy balance. If the arrow is being drawn in for Q, it's plus Q. If the arrow is being drawn out for Q, it's minus Q. And so when I ask a question like on an exam, if I say, what is the work output, right, I will want you to say blank kilowatts into the system or blank kilowatts out of the system. So sometimes you'll have to be a little bit flexible, especially when you're dealing with a heat exchanger, because you'll have heat going from one to the other process, and if you don't keep that nomenclature consistent, your math won't add up, right? You have to have heat going out of one and into the other, so it'll have to be minus in one balance and plus in the other. So I like to just make sure that the arrow direction doesn't matter. As long as your math is consistent, everything will work out. And if you screw up the arrow direction, all that's going to change is that it'll be a negative sign. That's it. Okay. So this is our process. So it's going to be a steady state cycle, which means that we can write the energy balance as du is equal to 0, which is equal to q dot c plus q dot h. So far, so good, which means that the heats have to balance. Any heat that comes in one has to be rejected to the other. Okay, so now let's do a second law balance. ds is equal to q dot c over tc plus q dot h over th, which has to be greater than or equal to 0. So if we substitute the energy balance into the entropy balance, we can get that q dot c is equal to 1 over tc minus 1 over th, which has to be greater than or equal to 0. So I substituted qc in for qh, then I pulled it out of the equation. Do a little bit more math. 1 over tc has to be greater than or equal to 1 over th. And then finally, th has to be greater than or equal to tc. So in order for heat to flow, it has to go from high to cold.
Correct me if I'm wrong, but as you further derive this, you also get the efficiency equation, right? For the rate.
Oh, you are just jumping the gun, because that's exactly what we're going to do right now. So the only difference between this and a Carnot cycle is that you're pulling work out. And so as a class exercise for the last about 10 minutes of class, we are going to derive the Carnot equation. Okay, everyone good on this page here? Okay, so the Carnot cycle, we have a cold reservoir, we have a hot reservoir, we have a heat engine, we have cold heat coming in, potentially, hot coming in, and work coming out. So who remembers the Carnot efficiency equation? What is it?
N equals 1 minus th over tc, or no, tc over th.
Bingo. So eta, the efficiency, we can write as W over QH. Again, we can write this as dots as well, or we could do it over a period of time and not have dots, for the rate is what I mean. We can also write this as 1 minus TC over TH. So we're going to walk through this as a class and derive this. But what I'm going to do is I'm going to have everyone take a few minutes and write out the energy and entropy balance. On the cycle. So that's the circle in the center. So do the energy balance and do the entropy balance on your own, and then we'll write it out and we'll do the next step. Okay, everyone's got the energy and entropy balance done? So the energy balance, du dt is equal to, what is our approximation, or what is this equal to? It's a steady state process, so this is 0. And then all we're doing is keeping tally of what's going in. So we've got QC plus QH minus W. That's our energy balance. So in this case here, W is equal to QC plus QH. Okay, so now let's do the second law. ds dt is equal to what? Is it equal to a number or a constant number? What is it equal to? ds dt is equal to?
ds would just be qc over t plus qh over t.
QC over TC plus QH over TH, and this is equal to 0. We're assuming no losses in this particular case. Technically, it's greater than or equal to 0. So then we could write that QC over T, QC over, I'll follow my notes so I don't make a mistake. QH over TH is equal to minus QC over TC. So now, to derive the Carnot efficiency, it's just a matter of substituting the first law into the second law and then rearranging it to get the Carnot equation. So we have, I'll just do that very quickly then. So we have QC is equal to minus QH times TC over TH. You then substitute that into, I'm going to go to another screen here. The work is equal to QH minus QH TC over TH. So then if we pull the QH out of the expression, move it over to the other side, we get W over QH, which is equal, actually what we're defining as the efficiency, is equal to 1 minus TC over TH. And we have the Carnot efficiency. All that was required is the combination of the first and second laws. Any questions so far on first and second law balances? Okay, we've got a few minutes left, so we'll prove, which is the other one? The Kelvin and Planck device wrong as well. In this one here, we have a hot reservoir, TH, QH. In this case, we could just write it as Q because there's only one in this apparatus. Cycle and work. Okay, so shout it out. What is du equal to?
0.
Okay, and what else? Q.
Plus W or minus W?
The way that I've drawn it is minus W. Okay, so in this particular case here, we will use this formula for the entropy balance, just because I think it's a little bit more interesting to disprove. So then that shows, if we rearrange this expression, that S dot gen, right, if we substitute this Q into here, right? Sorry, we don't need to do that actually. We just write S dot gen is equal to negative Q over TH. So what this tells us is that we can't have negative temperature, right? So that's a one-way street for the Q. You can take work, right? Work can go directly into heat, right? Because that's a negative Q. So that means if we draw the arrow going the other way, this works out. But we cannot have Q going directly into work. Otherwise, the amount of entropy generated is negative. So the only way that this equation here can be satisfied, right, is if the Q is actually going in the opposite direction. But we can't have a positive Q, as we've drawn it, and a positive temperature without having entropy generated being less than 0. So all of these historical statements of the second law are correct, but it's easier to go from a more general mathematical perspective that we use now, which is, ds, dt, and all that jazz. Okay. So that's what I've got prepared today for entropy. Any questions? So almost all of the homework, we're going to talk a little bit maybe about cycles and stuff, but generally most of the homework can be solved with just the first law and second law, open system balances, and then kind of relying a little bit on your past thermodynamics knowledge of where to get steam table information, how to integrate C sub P, and things like that. All right? I'll send out a Google poll so that we can get office hour times sort of locked in and question.
What is SGen again?
SGen is the rate of entropy generation. So in our case, we could write entropy as ds is greater than or equal to 0. Or we could also write, ds is equal to s dot gen, right, where s dot gen is greater than or equal to 0. So sometimes it's just nicer to have that variable, sgen, than having to rely on, these inequalities. Because I always get confused with inequalities too. It's like, okay, so if I times by a negative, I flip the arrows, things like that. So that's just the reason for that.
And so based on the second law of thermodynamics, you're setting that second equation equal to 0, right? And then you move the other thing over?
Yes, correct. Yes, you're right. This is equal to 0 because it's an open and steady state process.
Okay.
Yep, correct. Yeah, I skipped that step. Thank you.
So in so in steady state processes, the du is equal to 0 and the ds is equal to 0?
Yes. So in steady state processes, du dt is equal to 0, and ds dt is equal to 0. Anything dt is equal to 0 in a steady state process. And that's a good thing to bring up because a lot of people will make that mistake on like the first exam. Is they'll panic for some reason and think, oh my gosh, how am I supposed to integrate this ds dt term? When in many cases it's always 0. Because if you're dealing with a steady state process, and most of what we'll deal with is steady state processes. So in general, the dt term will always lead to 0. But that's a good point to bring up. So steady state means there's no time changes with temperature, pressure, composition, entropy, internal energy. Everything is time invariant. And you just have to balance out what comes in versus what comes out of the system.
Also, in thermal, you never really have steady state. It takes an infinite amount of time.
Correct. So a reversible process has to be done infinitely slow. And I think I guess it'd be Monday. I think we are going to derive how entropy is generated. Yeah. So on Monday's class, we're going to talk about what it means to be reversible and what it means to be irreversible. And basically, nothing we can do ever is reversible because anytime you have a gradient in the system, you have entropy being generated. That's a gradient in pressure, a gradient in temperature, a gradient in concentration. So all diffusive properties are entropy generating. So if I have a hot reservoir and a cold reservoir and I put them into contact, I've already created entropy. So the only way to do something reversibly in reality, where Sgen is equal to 0, is if I have an infinitesimally small gradient, which means it takes an infinite amount of time to heat something up. So if I wanted to heat up a pot of water on the kettle, that flame is a really high temperature, and that pot of water is really cold, boom, I've created entropy. So the only way to do it is to have, let's say it's not a flame, let's say it's an electric stove. Those elements on the stove would have to be just infinitesimally warmer than the water to transfer a little bit of energy very slowly as to not create a gradient. So a reversible process is inherently not possible. But we'll talk about how gradients create entropy on Monday. All right. And that's it. So please remember, I think it starts in a half hour. But on the east side of the MEB building, we're having the welcome barbecue. So we want all of the new students to be welcomed into the department.